Alrighty, welcome back to 105. So, more practice with linked lists, since typically that's the hardest topic on the exam. People tend to struggle with them. They are pointers. No way around that. So we can go over a few more exercises today. But before I start, any lingering questions or concerns or anything from the previous lectures on linked lists? All right. If that's the case, then we got a whole bunch of different functions we could implement. So we could create a whole bunch of functions that don't explicitly use nodes, that internally use nodes. So how you'd want to use this maybe in your program, you don't want to always deal with, setting the next pointer and all of that stuff. You just care that a value is in a list, yes or no. So we might create all of these functions for our program to use, and then we only create them once. We reuse them over and over again. So we could create a linked list create function that returns a pointer to that linked list type we defined earlier. Again, that would internally malloc things. Then here we would have a free that would go ahead and, like we wrote before, free every single node that we malloced and also free that linked list data structure itself. Then we could have some other helper functions like what we wrote before. Linked list empty, so returns whether or not a linked list is empty, true or false. The current length of the linked list, so how many elements are in it. We could have a function that prints us off the current values in the linked list. And what we wrote before, we could just write a function that adds an integer value to the front of the linked list. And then we could also write a function that removes an element from the front of the linked list and also returns the value that got removed from it. And some new functions we can write today. So a contains function, so that will tell you yes or no, whether or not a value is in a linked list. Maybe we have a remove first function, so takes a linked list and removes the first occurrence of that value from the linked list. And then maybe we have a remove all function, so it removes all occurrences of value from that linked list and returns how many occurrences it actually removed. So let's create our first function that just goes ahead and tries to that checks whether or not a value is in a linked list, yes or no. So again, this is the function we want to write. It should return true if val is in the linked list, false otherwise. So how would I write a function like this? So if this was on your exam, this would be probably like one of the easy questions. So whether or not a value is in a linked list. And just to make sure, you can scroll up to the top. So remember, the linked list type just has a pointer to a node called head. So that is the first thing in the linked list. And then each node itself contains a value and then a pointer to the next node in the list. So I'll go here. Yeah. Yeah, so we could define a current node. Usually we always have one where we iterate over and set it equal to where we starting. So yeah, the linked list head, so it's given by a pointer, so we can use the little arrow operator to access the fields, and that would be the linked list head. And then, yeah, so usually we do what we always do. So while current does not equal null, we're iterating over it. And then at the end, just so we don't forget it, we can do current equals current next. So that would give us the next element. So this time through the loop, we are looking at current. That is a node with a value. In this case, we can just look at current's value and see if it's equal to value, right? So if I do something like this, Did I mess up something other than that yellow squiggly line? Is what I wrote bad? Yeah. Yeah, that is an assignment, right? If I want to check if the current value is equal to the value I'm looking at, it's 2 equal signs. So, got to do that. And, well, in this case, we can end early. So if the current node's value is equal to the value we're looking for, then we can return true, right? We found it. If instead we made it to the end of the linked list and the current node's value never equaled value, we can simply just return false. So this is one way we can write the list contains function. Yeah. Yeah, that's okay for the linked list. So same thing we had in the previous ones. All right. Another way I can write that. So I just noticed this morning that, hey, this while loop looks like, hey, why did we learn for loops? Well, we learned for loops because it kept everything nice together where we cared about. So if we want to change this to use a for loop instead and put everything that has to do with iterating over a list in a single line, well, we could do the same thing. So we could do for and then set, again, as our first initialization statement, we can move defining the current node and setting it equal to there. And then what we're going to check is that current does not equal null. And then every time through the loop, we're doing current equals current next. So if I do that instead, I can do that instead of the while loop, and then probably looks a little bit nicer here other than it kind of scrolls. So now in my for loop, this initializes current. This is my thing I check at the end of every single iteration. Current does not equal null. And then here I update the value of current to point to the next one at the end of every single iteration. So this is probably a better way to write it because it really separates out what lines are used for me going over the linked list and what lines are dedicated for logic for actually testing whether or not the value in. But again, you can write it with a while loop if you really want. This one might be, I don't know, a bit more readable. All right, everyone good with that? All right, so, oops, our next function. We can write a function called remove first, which will be a little bit trickier. So in remove first, it should try and remove the first occurrence of that value in the linked list and return true if it got removed, false otherwise. Also, it should free the node used to store that value because we're assuming it's just disappearing. It's just being completely removed. So return. All right, so any ideas how we would want to go ahead and remove the first occurrence of a value? Yeah.
Well, you can just start by doing the same thing we did for finding it, what it contains.
Yeah, so let's first start by, well, we can just copy and paste this code. We always love copying and pasting. So we can do something like that. Let's just keep that value. So now instead here, if it matches, I want to remove this node. So how are we going to remove this node? Yeah, so this is going to be the case, whoops, where we probably need to keep track of the previous node, right? Because let's say we have something like this. So we have 1 that points to 2, that points to 3. Well, if we're removing the node 2, so say we're removing 2, then we need to change node 1's next pointer to point to 3. And that's about it, right? Which is the previous. So we probably need a variable to keep track of whatever the previous node is. And there'll be a special case here if we're doing it where if previous is equal to null, that means we're removing the first element of the list, so we probably need to special case it. So we could do that. So we could create a variable called int. Let's just do it outside of the for loop. We could do it inside, but let's not. So we could create a variable called previous, initialize it equal to null, and then, well, each time through the loop, we can update previous is equal to current. So each time through the loop, we're saying, okay, the previous node is now the current node we looked at for the next iteration of the loop. And the first time through the loop, of course, previous will be equal to null because it's the first one. So if we want to remove this node, if we go back here, order of operations is going to matter. We also need this pointer, right? So this pointer pointing to green is what we're going to save, right? Because we're setting the previous node's next equal to the current node's next. So if this is found, this is current, that is previous. So if we're doing it by hand, well, what we should be doing is basically saying previous, next should be equal to currents next. And that's the only line we really care about, right? So let's go ahead and do that. So I want to remove this node. So all I really care about the data from is that next pointer. So order of operations is going to be really important here. So let's just start off by just doing the normal case. So the normal case is we want to set, like we said, previous next equals current next, right? All right. Is that good? Is that all I need? Yeah. So we need to free the current after, sure, yeah, we can free current. That is definitely something we forgot to do. Could do that. Yeah. Yeah, the edge case, because, well, could be the first node, right? And if previous is null, that's a dereference of null, and our program is going to crash. So our edge case is if previous is equal to null, then what do we want to do? Yeah. Yeah, change the head, linked list head, to the current? To the current's next, right? Because we're removing current. So if the previous is null, we're removing the first element, we're updating the linked list head to point to current next. Otherwise, so we should put an else. Otherwise, we're updating the previous as next, like we said in the general case, to point to the current's next. And then we just free current, and then we're done. So, any disagreement with that? All right, looks pretty good now. So this is actually a slightly different way that we could do this problem that I did not have on the slides. So the solution I gave you with the slides, again, uses a while loop. And here, what it did was try and free as soon as possible. So it captured current next into a temporary variable just called next So we could immediately free current because we're not going to use current anymore. It's done. The only value we needed from it was its next pointer. So we could free it immediately, handle our edge case here, where in both cases, the only difference here, I saved myself some typing. Instead of writing current next 2 times, I just have to write next once. Again, does the same thing, and again, uses a while loop instead of a for loop. Again, completely up to you whether what you want to do. Both are correct. So good thing we saw 2 ways of doing that. So questions about that one? All right, that should make our next function really easy. So we can create a function to remove all matching values. So typo in the notes there. So we're going to write this function called linked list remove all. That should remove all occurrences of that value. And the function should also free every node that's used to store that value. So how would we remove every single occurrence of the value?
Just don't return true until, just keep iterating through.
Yeah, well, we already wrote a function that removes the first occurrence of an element in the linked list and returns whether or not you successfully removed it. So we can just use this function, right? We can just, while we've removed a node, just keep on removing a node. So it also says we need to, well, let's worry about the first case and just make sure we can remove nodes. So we can easily write, well, this is going to be a while loop. We don't know how many times we're going to go through it. So while we can use our function we wrote before, so while linked list remove first, so while we remove the first element, so again, this will keep on going over and over again until it finally returns false. If it returns false, hey, that means that value is no longer on our list. It means we've removed all of them. And that function we wrote already handles freeing the node and everything like that. So we don't have to worry about freeing multiple nodes. This function will do it for us. And if we wanted to keep track of how many nodes we deleted, well, we could just create a temporary variable called count or something like that. Initialize it equal to 0 because, well, if we end up not going into this while loop, we have not removed anything, so should just return 0. Otherwise, every time we go into this while loop, we have deleted an element, right? So we could do ++ count. We could do count plus equals 1. We could do whatever we want, whatever is clear for you. Again, it doesn't really matter. Or count equals count plus 1. Again, doesn't really matter. So, pretty good, right? Any questions about those fun functions? Probably be given something like that for the exam. So, we could actually solve some problems using linked lists. This is a bit of a silly one, but it's kind of fun with the functions we wrote. So, in general, you can actually implement more complex arithmetic using linked lists. In fact, some programming language runtimes do this. So you can sum together all values of a linked list by following these simple instructions that don't really look like they're summing together all of the values of the linked list. So what you could do is remove 2 numbers from the front of the list, add those 2 values together, and then insert the result to the front of the list. So every step of this process, we're removing 2 nodes and then adding 1. So it's getting smaller by 1 every single time, and it's actually computing the sum every single time. So if we repeat this process until only 1 element is left, then, well, what we're going to do is we're going to calculate when we're done by this, there's only going to be 1 number left, and that's going to be the total sum. So we can do something like this. So if we wanted to write this function, so we could go ahead, try and use our linked list. So we could create a linked list. Again, that would malloc and do all that fun stuff. Then we already wrote this insert front function. So we could insert 4, 3, 2, 1, and then print the linked list. So it should contain all those elements in order 1, 2, 3, 4. And then we'll write the sum function that should sum all the elements in the linked list and make sure that there's only one element left at the end. And then we'll print off the value we got from the sum function we wrote, and then we can free the linked list, make sure that everything is all good. So our sum function, well, should probably handle that edge case. We also wrote that empty function. So if the linked list is empty, simply just return 0. So the sum of nothing is 0. Otherwise, we can go ahead and just simply what we described on the slides before. So keep going while there's more than one element in the linked list. So I could just, again, write a while loop. So while the linked list length of the linked list is greater than 1. So while there's more than one element in the linked list, well, I also wrote a function called linked list remove front. So that will just return the value at the front of the linked list. Let me get rid of that. And then I could remove the element that is now at the front. After I've removed the front, there's a new thing at the front, so I can remove that. So now I have my two numbers, A and B. And now all I can do is just insert front. So I wrote this insert front, or we wrote this insert front function. So we can insert these elements to the front of the list, and what we can insert to the front is just A plus B. And then at the end, we know that there's only one element left in the linked list, so we can simply just return linked list remove front. So there should only be one element list. We'll remove the element in the front, and this function returns the value of the element in the front. So we can write a sum function that looks like that. It works. If we remember order of operations, well, you can actually write a calculator using something like this. But we compile it, we run it. The sum of 1, 2, 3, 4 should be 10. So if we go ahead and run it, hey, we get the sum is equal to 10. So again, how that's going to work. First time through this loop, it's going to remove 2 in front from the linked list, put 3 in the front. The next iteration of the loop, it will remove 3 and then remove 3 from A and B respectively. Then insert the value 6 to the front. The next time through the list, A will be equal to 6, B will be equal to 4. Then it'll add them together, add them to the front of the list, so our list will only have the value 10. And then the length is equal to 1, so we'll break out of the loop. Then we remove the front element, which is the only thing in the list now, so it will just return 10. So fun way of computing, well, fun, I don't know, weird definition of fun, but a way to compute the sum of a linked list without, I don't know, more creatively. So everyone understand how that kind of works? Kind of fun. Again, your definition of fun may be different than mine. All right, fun stuff that I saw on Piazza too. So you could also resize an array. So general rule of thumb in some courses, they'll just say, hey, if you're like adding to the front or adding to the back a lot, then you should use a linked list because you only have to do a constant number of stuff. But in reality, if you actually care about performance, arrays are generally a lot faster and use a lot less space. So arrays don't need to store pointers or anything like that, right? So if we're storing, I don't know, 6 ints, we only need to set aside space to store exactly 6 ints. If we're using a linked list, well, we have to store those 6 ints as before, but we're also storing 6 next pointers and also storing a pointer to the head. So we're using 7 pointers and 6 ints to store 6 ints. So arrays are generally a lot faster, even if you're removing elements from the front or the head, unless it is absolutely massive. So if we wanted to make an array longer. We kind of argued about before, how would we make an array longer in general? So say I only have like 5 elements in my array. I want to make it hold 6 elements. Uh-oh, did we forget arrays? Yeah. Yeah, exactly. Just make a new array and then just copy all the elements. And then, well, if you make a new array of size 6, copy the first 4 from the old one, you immediately made the array longer. So this is how we would do something like that. So we have to, of course, if we're using our friend malloc, we should check for errors and all that fun stuff. So we can assume we have a int array. It's just given by a pointer to an int that points to space for int length elements. So if we're trying to extend it, so we have this variable called new length, so we can create a new array that's at new length. We'll hold as many integers as we need for that new length. Check if malloc return null, meaning our computer's out of memory, meaning we're probably screwed anyways, but we can go ahead, make Valgrind happy if we want, free the old array, but then exit our program. Otherwise, and this also handles the case where our new array is shorter than the old one. So this min function will return the smaller of these two numbers. So this could also shrink the array if we really wanted to. So it will copy either if new length is greater than the original length, well, then min will return length. So we'll copy every single element we had from before. If new length is smaller, we'll essentially truncate it. So if new length is smaller than length, then it will return new length, and we won't copy every single element because there's not enough room. And then here is just copying all of the elements from the previous array to the new array. After that, I can free the previous array. I'm done with it. And then set array to point to the new array, set the length equal to the new length, and I am done. So could do that. You could write a function to do that if you wanted to, but turns out this function is already written for you. So resizing and allocation already exists in the standard C library. Some of you may have found it already. Some of you may not, but in case, here is the slide for that. So the function prototype, it's called realloc or reallocate array, and it takes a pointer as the first argument, and that is the same as the previous call to malloc. If the value of this pointer is null, this whole realloc function behaves exactly like malloc because you don't have a previous allocation to resize. And what it will do is it will return or try and resize the array to this new size where that is the size in bytes. So it will return null if there's an error and that pointer isn't freed. Otherwise, it returns a valid pointer to a new size bytes, and it will copy up to the old size if needed, if it didn't move. So the nice thing about this is it will not always copy some things. C might be able to just expand the original allocation, so you don't need to copy anything. It just reserves more memory from it, so no copying is needed. So it's going to be better than anything you can write because, well, it's keeping track of its own memory. You can't just magically make things bigger, otherwise it's undefined behavior, and we've already experienced how bad that is to debug. So we could use something like that. So if I wanted to use realloc instead of what I wrote before, the corresponding code would be, hey, new array equals realloc the old array with the new length times size of int. That was just the new size as before. Again, have to check if it returns null. If it returns null, I've ran out of memory. Bad things have probably happened. It also says that if it returns null, it doesn't free the pointer given to it. So we'll free array just to be nice and then exit our program. Otherwise, we successfully reallocated it, so we can just reassign array equals to new array, which we got back from malloc, and update the new length. Yep. Yep. Yeah, so if the new length is larger than the original length, it may copy it or it may just expand it and now it's memory you're allowed to use.
Oh, okay. So either way, we'll have it pointed to an array that's of the new length size.
Yeah.
And then we still have an array length.
Yeah. In either case, you'll have a new pointer back that is valid for that new size. That new pointer may start the same as the old pointer. You don't know. Yeah.
If it's smaller.
So if it's smaller, again, may return the same pointer, but now you're only allowed to use that new size. And C is allowed to reuse that additional space that was used before for other things. So it's, again, you have to make sure to not go out of bounds, and here you're updating the bounds, so you have to make sure to respect the new bounds. All right, so we can do something like that. So some of you have been, using malloc and just using values in there. Technically, that is undefined, so you are not allowed to do that. So there is a function that actually initializes memory for you. Its function prototype is, well, it's called calloc. Why is it called calloc? I have no idea. But it takes 2 arguments and also does the multiplication for you. So it takes num, so the length of, if this is an array, that's the length of the array. And then the second argument, the size, is the size in bytes of a single element. And like malloc, it returns just a void star, a void pointer. It's pointer to what? Well, you should know because you called me. So it takes 2 arguments, multiplies them together for you. And the only difference between this and malloc, aside from taking 2 arguments instead of and doing the multiplication for you, is that it is by design. It will initialize all the memory that it gives you a pointer to 0. So it will be guaranteed to be 0 initialized. So if you depend on that, your code will actually work. So if you use this to allocate a string, well, if you use malloc, you're going to get back random bytes. And if you use it as a string, who knows what's going to happen. If you calloc some memory and everything's initialized to 0 and you try and use it as a C string, well, it's going to hit 0 immediately. That is the null byte. It's going to terminate. It's going to look like just an empty string. So it's guaranteed to work and won't do anything terrible. So again, on some machines, like specifically your machines, if you're doing it on Windows or Mac for whatever reason, it may initialize values to 0 by luck. So if I have this code where, I define length equal to 4, and then I malloc an array, so just length times size of int, and I print my array, well, it prints off the 4 values in the array. On your system, you might see 0, 0, 0, 0 by complete luck, but likely on the testing machine, you'll see something like some negative huge values like this. While on the other hand, if I do calloc, and again, note here, length, comma, the size of, because it takes 2 arguments. So again, you don't have to do your own multiplication. So you do calloc length and the size of each individual element. And then if I print off that array again, given what I get back from calloc, I'm always going to see 0, 0, 0, 0, no matter what. So I don't have to bother to initialize it myself. Calloc will actually initialize it for you. I'd probably recommend using calloc over malloc, but again, up to you. It probably saves you, especially if your program kind of works, at least when you use it. At least when you use calloc, it will work on other people's computers. Yeah. Yeah, so the question is, can I set the initialization to any other value except 0? And the answer to that is not with calloc, but you can do that with some other functions. So I think there's functions called memset that will initialize the whole thing for you. So memset will just initialize it for you. So you still have to calloc or malloc to get some memory, but there's another function that can initialize the whole array to a single value. Yeah, yeah. All right, so another thing to look at. So another note here, another fun data structure is if you resize an array often, you may want to create what some people call a vector as a data structure. So a vector is basically a data structure, which is just an array that you can resize that just keeps track of its current length and current capacity. So you can just grow it yourself if you want. So capacity will keep track of how many elements could fit in this array. And again, it will just be a pointer we'll call data. And length is how many values are currently being used by that array. So in this case, you can just keep a current pointer and the length in the struct. You could just keep data and length in the struct if you wanted to. If you want to take this further, you can, again, keep track of capacity, which is the number of values we can hold without reallocation. So you might just ask malloc for a whole bunch of values ahead of time if you know you might resize it in the future, so that you're guaranteed that it will always stay the same. You won't have to change the pointer or anything like that. So to create it dynamically, well, we could create a function called vector create. Once you move on to C++ in 244, this is essentially what the vector is. So you can give it a length and it will create it dynamically. So it will malloc that pointer for you. So it will malloc space to hold that vector structure. In this case, I called it vector underscore t. That holds the pointer, the length, and possibly capacity. And then here we have to malloc the space for the array, which we are setting as the data pointer. So that would be mallocing length times the size of int, if we're assuming we just have an integer array. Again, check for errors. If null, or if malloc returns null, we're out of memory, we're screwed. And then we could initially set the length equal to the length and the capacity equals to the length as well, because, well, that's what we got back from malloc. We didn't ask for more memory, so that's all we can use. Yeah? Sorry? So so the question is, when is the capacity not the same as length? So that's up to you and your program. So for some programs, it might be worthwhile to like, hey, let's ask for length times 2, so we have room to grow. And then you can write your, resize function to just check the capacity. If it can hold it, just update the new length and then you're done. You don't have to reallocate or do anything like that. So it's kind of up to you. In this case, I'll just assume the capacity is the same as the length, but you could change it if you want. All right, so yeah, our resize function. So if we want to resize the vector, reallocating if needed, well, we could check that new length next to our capacity. Again, we could set aside more space. If we know ahead of time, it might grow. It might be useful for some programs. If the new length is less than or equal to our capacity, well, we don't have to do anything, right? We can just update our length to the new length because, well, our array is actually valid for that, so we don't have to actually realloc anything. Otherwise, we'll call realloc, give it the pointer to our data with the new length times size of int. So I'm asking for it to expand the array or possibly shrink it. And then again, like we did before, check if data is null. If it's null, our program ran out of memory. Otherwise, update the length and update the capacity. And again, this is just what I'm choosing to do for this thing. You might set aside more space. If I just grow it, then maybe I want to set aside like more room or something like that, because maybe I want to control, that realloc function. That's a call to the C standard library. It may or may not move that array. If I want to guarantee that it doesn't move it, I have to set aside capacity. Again, it will depend on your program. All right, thing we can start, I guess. So this is a final from, I guess, 3 years ago. So write a function called reorder. The prototype is given below. This is going back to linked list that reorders the nodes in the linked list such that the nodes of the value with the value 0 appear at the front of the linked list, and the nodes with any other integer value appear at the end of the linked list while maintaining the original order of non-zero nodes. So for example 1, if my linked list, there's an implied next between everything. So if it goes 0, 0, 15, 0, 0, 13, 10, well, all of my non-zero nodes should stay in the exact same order. So it should be 15, 13, 10, and all of the nodes with the value 0 should go to the front. And then the next example is, well, if it's 1, 0, 19, 0, 0, 5, 0, well, it should be 1, 19, and 5 at the end in that order, and all of the 4 zeros should move to the front. So it also says you are not allowed to copy or modify a data member of any nodes in the linked list. However, you can modify the next pointer in the node. So that's preventing you from just iterating through it, counting how many zeros are there, and just straight up deleting them, and then recreating a whole bunch of them only at the front. So I'll give you a minute to think about that, and then we can take it up. So you just are given, you're supposed to write the function called reorder that just takes a linked list. You can assume, again, they like doing the more C++ style of names. So they call it linked list with capital letters. I usually like all lowercase with underscores between them, ending in _T. It's usually what C programmers do. This is usually what C++ programmers do. But again, kind of a style thing. So have you think about that, and we can try and implement it and see how we go. And are you allowed to write helper functions? Yeah, on any final question, you can write helper functions. All right, any ideas how we would do this? Yeah.
I have a full solution. Maybe what I would start with is like you start at the head, and then you keep going down until you reach the first non-zero number,
Yeah.
and then next to that non-zero is the pointer to the next non-zero number. And then like that way, I guess you can link all the non-zero ones together.
So you want to start at the head, so
Yeah.
probably have something called current like that. Then go to the first non-zero. Yeah.
And then current dot next.
So current next, so you want to change this to,
To the pointer to the next non-zero.
so you want to change it to the next non-zero. So we'd have to go till we find this and then have another search that starts in this part of the list. Yeah, so if we did do that, how many pointers would we change? So you'd probably need a previous, right? Or would we? So what you want to do is essentially, we're taking that, let's say 0, and what you want to do, the final part, what you want to do is you want 15, next pointer to point to 13, and 13 points to 10. But what you want to do in between, so you want to take 15's current next pointer, right? What should be pointing to that node? Yeah, what should now be pointing to that orange? What should be holding that orange pointer now? No, the orange should be pointing at that 0, right? But who should, in the new list, what should be pointing at that node? Sorry? 13. So you want 13 to point to that. Yeah, so you might be like, oh, okay, well, if we went through all the pointers, right? So yeah, you're right. So current, so this is current. So this is current next. Or sorry, that's what you want update current next equal to, right? And this is currently current next. Let's do it. So what should be happening is the previous node here should be pointing to current next, right? So this old orange node, it should be this one. So, and then now we also want to change, well, we don't want to change what it's pointing to, but now we're kind of in a catch-22 because we want to update this one to point to node 13 as well, right? Which means we would have to search for two things. We'd have to search for that's the last 0 generically, right? We'd have to search for the last 0 and then the first non-zero number. We could do that. That might land us in a bunch of edge cases. We could do that. That might work. We only have a minute, so you'll probably be taking this up yourself. But one idea that you could have is just simply, well, any 0 I find, if I iterate through current, any 0 I find, I can just move it to the beginning of the list no matter what. So in this case, this is kind of an edge case where it's already at the front of the list. I don't have to move it. This, oh, it's a 0. I could just move it to the front of the list if I wanted, like that. It's a 15, leave it alone. Next one, it's a 0, move it to the front of the list. Whoops, took too much. Next one, not 0, leave it. Next one, non-zero, leave it. And then, hey, it'll just be updated like that. So that's another way you could think of it. That might be a bit easier, but we are out of time. So just remember, pulling for you, we're all in this together.